Here we have the first law of motion. Now, in the first law of motion, objects at rest stay at rest, or objects in motion stay in motion at a constant speed in a straight line when and only when the forces are balanced. That is, the net force is equal to zero. Now take a look at this. We have an asteroid moving through space at a constant speed. Now there are no forces on this asteroid. Because let's look at the force diagram. So the force diagram, there's nothing, right? Because we know the only thing that's keeping the asteroid moving at a constant speed is inertia, right? So there's no forces, and there are, well, no forces in the x or y direction, so it's just, again, inertia keeping it going at a constant speed. Now, this is an example of literally no forces, right? Now look at this. We have a globe, and on this globe, it's magnetically levitated. You have weight pulling it down. I'm assuming this globe is on Earth, and there's a magnet up here holding the globe in place. Now, these forces are balanced. The net force is equal to zero, so there's no force in the x direction for sure. But in the y direction, you have the force of magnetism up and the force of weight down, and these two forces, since they're the same amount of force, they balance each other. So the net force is equal to zero. So this example, too, satisfies Newton's first law, because despite there being forces, the forces are balanced, and the forces add up to zero, so it stays at rest. So that is Newton's first law. The first law is all about when the net force equals zero. And when the net force equals zero, objects stay at rest or constant speed, and that's it. Now, looking at the second law, so there is an acceleration when there is a net force. So the second law is about when there is a net force. And when there is a net force, you will have an acceleration. Objects accelerate in the direction of the net force. So that's pretty simple, right? It kind of makes sense. And lastly, acceleration is inversely proportional to the amount of mass. It's basically just saying as objects get heavier, not really heavier is probably not the best word, as objects get more massive, you have less acceleration. Look at this rocket right now. The rocket's completely at rest in space. So it's actually kind of obeying the first law right now more than anything else. And there's literally no forces acting on the rocket. So you have nothing. But the moment we turn the rocket engines on, there will be exhaust coming out of the back of the rocket. So you have gases, etc., coming out of the back of the rocket, and what pushes the rocket forward is the thrust. So, ready? 3, 2, 1, go. So you can see now that the rocket's on, you have a force of thrust. Now let's write the new equations. Now in the y direction, you have no force, right? The rocket's not doing anything in the y direction. It's simply going left to right. But in the x direction, you have one force, and one force only, thrust. Now here's the difference from the first law. In the second law, anytime something is accelerating, you're going to set it equal to ma, right? Because the net force, according to Newton's second law, if you look at this equation right here, if you solve this for net force equals m times a. So set it equal to ma. Now we're going to be examining the second law using this very simple problem because there's only one force, you're in space, so you can clearly see the effects of the first law. The second law, rather. Now, the second law of motion says this. Now, let's say for the sake of simplicity, the rocket is 1 kilogram. Now, the rocket's 1 kilogram, and we have a thrust of 1 newton, you will have an acceleration of 1 meters per second, because that is what 1 newton is. 1 newton is defined as 1 kilogram meter per second squared. So 1 newton, again, is the amount of force necessary to accelerate just 1 kilogram at 1 meters per second per second. And don't forget what acceleration is. So when we say you need 1 Newton of force to accelerate something at 1 meter per second squared, what we're saying is every second the velocity goes up by 1 meter per second. So 0, 1, 2, etc. So that's a pretty simple example, but let's make it more interesting. Let's say the rocket has a constant thrust of 18 newtons, but we increase the mass of the rocket to see how it affects the acceleration. So if we have 18 newtons and the mass is 1, well, the acceleration is 18. Let's make a point. Let's increase the mass, actually let's double the mass to 2, and look what happens to the acceleration. It gets cut in half. So you can see it's a dramatic difference, and we plot the point. Let's further increase the mass to 3. And the acceleration is, well, 6. So you can see as we're increasing the mass, the acceleration is going down. And I think that just makes sense, right? The more massive the object, the less acceleration you have, especially, well, if the thrust is constant. So we can keep doing this, right? You can see that the acceleration keeps going down and down and down. And we can plot a line here, more so a curve. So you can see the acceleration is inversely proportional to the mass. So we have the acceleration equals the net force. The only force on the rocket is thrust, so it's the thrust divided by the mass. So take a look what happens as we increase the mass, right? The acceleration goes down. So right here, as you increase the mass, the acceleration goes down. And I think that just kind of makes sense. So that is the second law as you change the mass. Now the third law of motion, you're probably familiar with. For every action force, there is an equal but oppositely directed reaction force. Now all forces come in pairs. There is no such thing as a solitary force in the universe. And what we mean by that, think about this. If I push a car, right, the car is going to apply a force back on me. So there's a car and me, right? There's a force on the car from me and a force on me from the car, right? It's two different objects, me and the car. So all forces will come in pairs. And even if they're distant, like look at the sun and the earth, they're quite distant. They're 93 million miles away. There's a force on the sun from the earth, and there's a force on the sun right back and forth, right? So that's the thing to realize. They always act on different objects, right? So there's a force on the earth and the sun, and there's a force on the sun from the earth, etc. So let's look at a few examples to really cement this. Now, if we have a person standing on the ground, the person, of course, has weight. And the person has a normal force on the person from the ground, right? It's a pretty simple diagram. Now, these two forces are equal, especially if the person is just standing perfectly at rest. Now, we're going to be drawing the force diagram for the ground. Now, on the ground, there is a normal force on the ground from the person. So you can see that these two forces shown in yellow are equal. These are action-reaction pairs. So that's action and reaction, right? And it actually really doesn't even matter which one you call action-reaction, you know? The more important thing to realize is all forces come in pairs, and they're the same amount of force, right? So if the person has a weight of, say, 800 newtons, this normal force is 800 newtons, and the person is applying 800 newtons back and forth on the ground, vice versa. So let's look at a more interesting example. Let's say we have a cannon launching a cannonball, and we're going to be examining the forces the very moment the cannonball is launched. So, 3, 2, 1, yeah, there we go. So you can see the cannon has a recoil, right? Now, let's examine why. Let's first draw the force diagram on the ball. Now, here's the thing. When you draw the secondary force diagram, it is true that the cannonball has its own weight. There's probably a normal force on the cannonball while it's still in the barrel, etc. But let's just focus on the action-reaction pairs. So there is a force on the ball from the cannon. Now, you can be more specific. There's like the force of the explosion as you are launching the cannonball, but there is a force on the ball from the cannon, and the reaction is there's a force on the cannon from the ball. These two pairs are the action-reaction pairs. So this force right here, when you launch a cannonball, explains why the cannon recoils. So, and you have a little bit of friction. That's the reason why the cannon doesn't endlessly just keep going backwards forever. But think of it this way. The cannon has a lot of mass. The cannonball has very much less so, right? The cannon could weigh 1,000 pounds or maybe 2,000 pounds, whatever it may be. So they have the same amount of force. So a cannonball gets thrown off at some tremendous acceleration, perhaps like 50 meters per second squared, whereas the cannon, not so much, right? The cannon has so much more mass, it has so much more inertia that even though there's still a great amount of force on it, it resists the motion. So that's why it only recoils a bit, whereas the cannonball goes off quite the distance. So that is a classic example in physics. Now, let's look at something more in outer space. We have two asteroids in space, and it looks like they're going to collide. They're going to collide, and there they go. They collide. Now, before they collide, there are literally no forces, right? They're just moving in space due to inertia. But the moment they collide, there's going to be a normal force on asteroid A from B, and there's going to be a normal force on asteroid B from A, and those two forces are equal. So the normal force may only exist for seconds as they collide before they bounce off each other, but for that very brief amount of time, there is a tremendous amount of equal and opposite forces on both asteroids. So there's a lot of force because you've got two massive asteroids colliding in space. But let's change this example. So instead of two massive asteroids, let's make one much smaller. Now, right now, before they collide, again, there are no forces on these asteroids. But look at this. Here's the difference. You still get a normal force on A from B and still get a normal force on B from A. And yes, they are equal forces. But here's the difference. See how these normal forces are much smaller than before? It's because asteroid B is far less massive. And because asteroid B is far less massive, when they collide, asteroid B really doesn't have that much inertia. And it can't really resist as much. So you just don't have as much force. It's like if you're driving down the road and you hit like a bug, yes, there's a force between the windshield and the bug and the windshield, right? An equal amount of force, but it's really not that much force. Your car is a massive object barreling down the highway at 65 miles an hour, and it hits the bug, and there is a little bit of force, but not that much. But, if you were driving down the road and you hit a dragon, right? A dragon has lots of mass. That would be bad, right? So there you go, right? So all forces come in equal and opposite pairs, but only as strong as the weakest object can exert back. So there you go. These are Newton's three laws, and they really tie up all of motion. And with that, it brings us to the end. So that's it.